Hello everybody. Today we are going to be working on, in our calculus course, we're going to be working on vector and parametric equations of a plane. According to our Google Classroom, this was lesson 4 in unit 3. So we're going to complete the lessons 4 and 5 in that unit this week, and also do a lesson from intersections of lines and planes to finish off vectors. So before we get into the lesson, I just want to do a quick review of what we did in the first 3 lessons of Unit 3, just to get you familiar again or reacquainted with these equations. So if you remember, lessons 1, 2, and 3 were equations of lines. First we did R2, which is two-dimensional, just x and y coordinates, and then in R3, which was x, y, and z coordinates. So we started off with the vector equation of a line in R2. So the basic vector equation would be looking like this, where the vector to a point on the line called R, the vector is called R to any point on the line, starts off with a position vector that goes to any point on the line, and then we add a scalar multiple of the direction vector. Okay, t is a scalar, it can be any real number. R, R naught, and m are vectors in R2. Okay, so if we put this in component form, basically we're just changing vector r to a vector with components x and y. The position vector, we have x naught, y naught, which is a point on the line. And then we have our direction vector, which we always call m, and the components of that we call a and b. So that's just breaking these into component form. And so that's traditionally what the vector equation looks like. If we expand the vector equation, the left side's the same. We've got the x component will be x naught plus ta, and the y component will be y naught plus tb. So we've just broken that into a single vector here. Okay. Now, once we have it in that form, it's very easy to create parametric equations. So we take each component, we say x is equal to this, x naught plus ta, and y is equal to that. So very straightforward from that version. We get the parametric equations, and then once we have parametric equations, we basically isolate each of these equations for t. So basically for the first one, we get t is equal to x minus x naught over a. And the second equation would be this version. Both of these are equal to t, but we usually don't include that part in the symmetric equations. Okay. And then the last thing we did was a Cartesian equation, which looks more like a line that you're used to prior to vectors. There's no vectors. It doesn't look like there's any vectors here. We have ax plus by plus c. In this case, the a and capital A, capital B, that's actually the components of the normal to this line. And we use capital A and B for that, and it is related to the direction vector, or a direction vector, if we just switch the components in the order and make one of them negative. That also becomes one of the possible direction vectors. And if we do a dot product of direction vector and normal, we get 0. Okay, so that was everything we did in R2. So if we look at R3, all we're really doing is adding a y component to all the vectors. So this looks exactly the same in this form as it did in R2. But when we break it out into components, you see each of the vectors has a new z component as well. So for the direction vector, we have added this c value here. And then when we expand it, we get that additional component here that we didn't have in R2. Okay, and then when we do the parametric equations. The only new thing is that z value there. These two would be the same as the two that were above here. We're just adding the third component for R3. And then when we do the symmetric equations, same idea. We isolate each of these three for t. This one here is new, which basically comes from isolating t in this equation. Okay, so we have three parts to the equation now for the symmetric equation, whereas before we just had the two parts for the x and y. Okay, and then we didn't spend a whole lot of time on this, but there's also Cartesian equation in R3. The difference is we have this new term in here, CZ. Okay, so the C gets added on to the normal, because the normal is now a R3 normal. So you have capital A, capital B, capital C are the components of the normal. We have this looks like it's new, but really it was just replaced. We just renamed C to D down here because we needed to use C for our Z component there. So again, if you dot product the normal and the direction vector, you'll get 0. So there's lots of different ways of getting a direction vector from here. Okay, so that's what we did before the break. So what we're doing today is lesson 4 here. Vector and parametric equations of a plane. So everything we just reviewed was to do with lines. So a plane, it's important to understand a plane is a two-dimensional surface that's flat, and it's a surface that extends infinitely far in all directions. When we draw it, we usually draw it as part of the plane, because obviously if we drew it completely, it would have no edges to it. So we just draw part of it so we can understand it a bit better. And what we do for planes is we use the symbol pi to label a plane. Okay, I'm not sure why that's used, but that is the symbol. We use L for lines, pi for planes. Okay, the big difference with planes is, maybe I'll start down here with this diagram. I'm going to zoom in a bit. Okay, so this is a pretty good diagram. So the outline in the blue, the parallelogram there, that's the plane that we're trying to define. So again, just like a line, the way we define a plane is we have a position vector, which is this r0, which goes from the origin up to any point on the plane. It could be any point at all. So this could be an infinite number of position vectors. And then we have, if it was just a line, we'd add a direction vector to define the line along there, but this is a plane, so we have to actually have two different direction vectors. It's a little bit hard to see on this, but there's a yellow direction vector called A here. Maybe I'll just darken it a bit here. So we have two direction vectors A and B, and together those define the plane in question, and we start those two from the position vector that gets us to that point on the plane. Okay, so if we go back to the key concepts here. Okay, so in R3, if this is our position vector that gets us to that point, x0, y0, z0, we need that to start off with, and then we have two different direction vectors that are needed for the plane. We call them A and B in this case, and the components are A1, A2, A3 for vector A, B1, B2, B3 for vector B. Then if we create a vector equation, it looks really similar. Well, it looks quite similar to the direction of a line in R3. The difference is we've added on this second part here, the second direction vector, with another scalar. Okay, so we actually have to use two scalars now, s and t, one for each of the direction vectors. Okay, so that's our vector equation. And then if we break these down into the x, y, and z components, we can get our parametric equations. For example, x is equal to x naught plus SA1 plus TB1, and similar thing for y and z. I think I forgot this should also be t as an element of R, both s and t. Okay, and the interesting thing here is there's no symmetric equations for a plane, so that might be good news for you. But basically, since now we've got two variables or two scalars s and t, it's going to be very hard to set. It's going to be hard to isolate for s or t and then set them equal. So we don't do symmetric equations. Okay. Now there's a lot, just like lines, equations of lines, where there's an infinite number of correct answers. It's also going to be the same thing with planes. Okay, there's an infinite number of position vectors, and there's also an infinite number of direction vectors that can be used. So you may have a totally correct answer that looks completely different from somebody else's or the answer in the book, but they both can be correct. So just be aware of that. So if we're going to come up with a equation of a plane, there's different inputs we can use here. So eventually we're going to need two direction vectors and a position vector, but you could be given any one of these four situations, and we're going to have some questions on the next page that guide us through this. But you could have, in this case, you've got a line that's defined and a point that's not on the line. If the line and the point define a plane, we can come up with the equation of that plane. Okay. Now obviously that point can't be on the line, otherwise it would just be a line and not plane. Okay. Second situation, you have two lines that intersect at a point, and you can kind of see here each line will be its own direction vector, and probably the intersection point would be the position vector. Okay, part C, this is a pretty common one. You're just given any 3 points in R3, and you'll be expected to come up with the equation of that plane. What we would do for that is create two direction vectors using A, B, and C. You've got 3 choices, well really 6 choices. You pick 2 of those and use one of the 3 points that you're given as your position vector in your equation. And then the last one, this is probably the rarest one, you got 2 parallel lines that do not touch, but you can kind of see that they would create a plane. So that's the fourth and least common situation. Okay, so again, we've got at the bottom of the page, we've got all the different equations that we talked about in the key concepts. Okay, so let's zoom back out a bit. We'll do our autofocus. Okay, so for this question, again, everything on this page, we're going to create the equation of the plane from the different situations. So in this case, we've got 2 intersecting lines. Okay, and you can kind of see that, well, the points, the position vectors aren't the same. The 2 direction vectors are not collinear. They're not scalar multiples of each other. So they're definitely not parallel. So, but they do apparently intersect. So we can't tell that just by looking at them that they intersect. We could prove it, that's exactly how we're going to start this. So the first thing we're going to do here is find where these 2 lines actually intersect. So find the point of intersection of L1 and L2. Okay, and what we're going to do is use the parametric equations for each line. So if we look at each of the, so for line 1, x would be equal to 1 plus 2t, x equal 1 plus 2t, y would be equal to 2 plus 3t, and z would be equal to 3 plus 4t, 3 plus 4t, and then we do the same thing for line 2, L2. So we get x is equal to 2 plus s. We get y is equal to 4 plus 2s. And z is equal to negative 1 minus 4s. So what we're going to do here is find the values of s and t, hopefully, that would allow us to have a point that's in common between these two lines. So the way we do that is we pick two of the x, y, and z. So I'm just going to start with x. So I'm going to say, well, if they have a common point, then 1 plus 2t must be equal to 2 plus s. And also at the same time, if we do our y's, set them equal to each other, that means that 2 plus 3t must be equal to 4 plus 2s. Okay, so what we're going to try to do is come up with a more simplified equation that we can work this. So for sure we're going to combine the constants here. So I'm going to subtract 1 from both sides. I'm going to get 2t. Actually, I'm going to subtract 2 from both sides. So I get 2t minus 1 is equal to s. So that gives us a good equation to work from. Let's see what we can do here. So if I subtract 4 from both sides here, I'm going to get negative 2 plus 3t is equal to 2s. And since I've just kind of already figured out what s is as a function of t, I'm going to change the s here to the 2t minus 1. So now I've just got an equation with t's in it, so I'll be able to solve for that. Negative 2 plus 3t is equal to 4t minus 2. And if I simplify that, subtract 3t here, and if I add 2 to both sides, those actually cancel out. So I basically get that t is equal to 0. Okay, and then if I use that back here in this equation, change t to 0, I get 2 times 0 minus 1 equals s. So that's s equals negative 1. So for the x and y components, I can set s to negative 1 and t to 0 and get common x, y points between them. So now that doesn't prove that there is a point of intersection. What we have to do now is check for the z component. So if I look at from the first line, z is equal to 3 plus 4t. Well, t is supposed to be 0 for the other two, so we plug that in. We get that z is equal to 3. And for the second line, we've got z is equal to negative 1 minus 4s. S is supposed to be negative 1. So that's negative 1 plus 4. That's also equal to 3. So the fact that the z values also match for these two, the values of s and t that we got, that tells us that there is a POI. So I'm going to use t equals 0, s equals -1 for the POI. And that tells us that the POI is actually, the point of the POI is, if I plug these in, let's see, if I plug the s and the t in, you'll see that we get 1, 2, 3 as our point of intersection. So we've got our point of intersection. So that can be our position vector. So our equation, I'm going to start using the pi symbol for that plane. So that plane equation is equal to, now I can use this, like we said, that could be the position vector 1, 2, 3, which is what I got when I subbed in t equals 0, s equals -1 into the parametric equations. Now I need my two direction vectors, and I simply get those from the original two lines. These are not collinear, they're not parallel, so I can just use those directly. Now, I have to make sure I use two different values for our scalars. So the first one would be 2, 3, 4. The order here doesn't matter. And the second one would be 1, 2, -4. So that is our equation given two intersecting lines. This is how we would do that. Okay, so the second example, this is a more common situation. You've just got 3 points. Now they're non-collinear, which means they don't form a straight line. They actually form a triangle in R3. So all we really have to do here is come up with two direction vectors from these 3 points, and I have 3 or 6 possible direction vectors from here. So if I looked at BC as a direction vector, so BC, you start with the C component, subtract the B component. So it's 2 minus 0, -1 minus 1, and 0 minus -1. So that's our direction vector from B to C. And then we could just choose another combination of points. I'm going to go DC just because I'm going to get some positive values here. So when I create DC as a direction vector, that's 2, -1, -1. If I was to have gone the opposite order, CD, these would just be flipped in sign. It'd be -2, 1, 1. Okay, either one of them is okay, and that's why I say you've always got 6 different direction vectors. You got 3 combinations of 2 points, and you could go in either direction. So now that I've got my 2 direction vectors, there's not as much work involved for this one. The equation of the plane is going to be, now here, the position vector could be any one of these 3 points. So you have lots of options. I'll just pick, I'll pick the last one there, D, but it can be anything you want. Any one of those 3. You can't change the signs on these. It has to be exactly the same. And then we just do scalar multiples of our 2 direction vectors, 2, -2, 1, which is our direction vector for BC, and then a second scalar t with our second direction vector. And that is the equation of that plane. Okay, that one's pretty straightforward. Just create your 2 direction vectors and make a position vector from one of your 3 points that define the plane. Okay, the third one is a line and a point that's not on the line. So if we go back to our first page, that would be the case A here. We've got a line and a point that's not on that line. We need to find the equation of that. So in this case, we've already got a direction vector here. What we do need, and we've got a position vector to get to the line on the equation of the line. So what we're missing is a second direction vector, second dv. Okay, so we've got this point. We definitely have to use this point. We've got a point on this line. So it's just doing a, I'm not sure what you'd label this point as. If that was B, it'd be a AB or BA. So if we do the subtraction there, we're going to get, I could subtract this way. So 1 minus 0 is 0. Sorry, it's 1. 2 minus 1 is 1. And negative 1 minus 2 is negative 3. So that's one of the direction vectors we could get. The only other one that you could really get from here, well, directly from here, would be if we subtracted the opposite order. So we get negative 1, positive 3. So either one of those would be fine. So now we've got everything we need for the equation of the plane. We've got our position vector from the original line. We've got our original direction vector from the line. And finally, the second direction vector that we just created here from between the point and a point on the line here. So that would be 1, 1, negative 3. Okay, so that's the equation in that situation. So these two, there was no whole lot of work to do, just create direction vectors and use the information that was given. This one, obviously, more work to find the POI first. Okay, this one here, this is our fourth case. This is the one that probably won't see all that often. It's a case D where you have two parallel and non-coincidental lines. They're not the same lines, and you can see they're parallel by the direction vectors here. If you just multiply one of them by negative 1, you'll get the other. So you can see they're parallel just by looking at them. So again, we've got a direction vector. We could use either one of these. What we do need is a second direction vector, just like above. Okay, and the best way to get those would be to, let me think here, let's subtract our two position vectors. These are 2 points. So 1 minus, we'll call this M. 1 minus 3, 2 minus 4, and 1 minus 0. So that's a direction vector between those 2 points that make the position vectors. So we've got our second direction vector. We've got 2 choices of position vectors and 2 choices for the other direction vectors. So this one's pretty straightforward. Again, I could choose either one of those 2. I'll choose the first one. That's my direction vector. Again, for the direction vector from here, I could choose either one of them. I'll pick the second one because they're positive numbers. And then the third one, again, I could also have done it the opposite order. I got 2, 2, negative 1. That'd be fine. I'll just stick in what I calculated. Okay, so there is your equation of that plane. So we covered all 4 situations from the first page of given information, and now we know how, for each of these cases, how to come up with the equation. Okay, if we go to the next page. Okay. Okay, so in this case, we're going to use an equation of a plane to get additional information about the plane. So in this case, we've got the equation of the plane here with our two direction vectors and our position vectors. We want to just get 2 points on the line. There's a variety of ways of doing this. I think maybe the most efficient way and procedural way would be first start off with the parametric equations. So we've got x equals -1 plus t, y is equal to 2s, because the other ones are 0, and z is equal to 2 plus s minus t. And then what we can do is just create a little table here. Okay, so the first part of the table on the left here, that's going to be our s and our t values that we just randomly pick, and then that's going to give us x, y, and z values from the parametric equation. So you could really pick any values of s and t you want here. I wouldn't use 0, 0, that's not going to work. But let's go with 1, 1, and 0, -1. If we plug these values in to these equations for x, y, and z, we're going to get 0, 0, 2, 2, and -2, 0, 3. So these two are 2 possible points on the line. So 2 points on the plane. Now we can use our round brackets here because these are actual points and not position vectors. -2. Now again, you can come up with an infinite number of points, because there are an infinite number of points based on different values of s and t, which are also infinite. So lots of possible solutions there. So find a line on the plane. Okay, so if we go back to the equation, we've got our position vector and then our 2 direction vector as well. I could get a line from here just by maybe making s0 or t0. Okay, and what that would do would be create basically create an equation that's got a position vector and only one direction vector. Okay, because the one turns into a 0 vector. So in this case, obviously use the same position vector, although we could have also used position vector from one of the 2 points we just got, but this will be a bit safer because you know it's correct. And then say we made S0, then that's going to knock that completely out, and we're just left with, sorry, this should be a plus t 1, 0, -1. So you can tell this is a line because it's only got one direction vector. Okay, I could have also picked instead of using t times that, I could have just picked s times s is the scalar and 0, 2, 1 is our direction vector. That would also work. Okay, last question. Find the vector equation of a line that passes through the origin. So obviously this is in R3, so that would be 0, 0, 0, and is perpendicular to this plane. So the fact that it's perpendicular to the plane, now this plane is the plane up here, just so you know. So so if we want a line that's perpendicular to the plane, what we're going to do is the cross product. So the direction vector of the line we're looking for, that's going to be the cross product of the 2 direction vectors. And so that's the 2 direction vectors we were given. So basically that's going to be 0, 2, 1 cross product with 1, 0, -1. And if you do that, you're going to get -2, 1, -2. So that's the direction vector of the line that we're trying to get. And the point that we know is 0, 0, 0. So a direction vector to that point, well, that's really just a 0 vector. Okay, so we don't even have to put a direction vector, which means it just starts from the origin. So our line is actually quite simple. There's no position vector because it's the origin, and then we just use a scalar multiple of this direction vector that we just found using the cross product. Okay, so that's the lesson. Basically, we looked at first example looking at how to create equations of planes, and the second example was how to use the equation to come up with other information. So I hope that helps you out.